welcome back. So when we think about grouping data, right, we usually picture finding the center of a few nice, neat, round blobs. But what if your data isn't so simple? What if it has curves or rings or other really complex shapes? Well, today we're diving into an awesome algorithm that finds the true shape of your data, not by looking for centers, but by understanding how crowded it is.
Just take a look at this. On the left, a super common algorithm called k-means is, well, it's having a really bad day trying to figure these data sets out. But on the right, another algorithm, DBSCAN, absolutely nails it. Perfect score. So what's the difference here? Why does one fail so spectacularly where the other just gets it? Let's find out.
To really appreciate why DBSCAN is so powerful, we first have to get why the more traditional methods can sometimes fall short. So first up, we're going to see exactly why simple clustering can lead us down the wrong path.
Okay, so k-means. It's a fantastic tool. It's used all over the place, and its logic is pretty straightforward. You tell it how many groups you want, it finds the center points or centroids for them, and then it just assigns every data point to whichever center is closest. But, and this is a big but, its biggest weakness is that it's built on the assumption that all your clusters are basically round, like spheres. It's always looking for blobs. And this picture just illustrates the problem perfectly. The moment we give k-means a data set with these cool spirals and lines, it gets totally lost. I mean, look at how it's grouping those blue points from the outer spiral with the yellow points from a completely separate shape. It's just doing what it was told, find a near center, and it's completely missing the obvious structure that we can see with our own eyes. So if looking for the center of a group doesn't work for this kind of data, what's the alternative? We have to shift our thinking completely. Let's stop asking where's the middle and start asking how crowded is the neighborhood. And that brings us to DBSCN. The name really says it all. Density-based spatial clustering of applications with noise. Yeah, it's a mouthful, I know. But the key phrase you gotta remember is density-based. Instead of looking for centers, it looks for areas where points are packed together really tightly, and it connects them to form clusters of literally any shape. The secret sauce to DBSCAN is how it defines a neighborhood. It goes through and classifies every single point in the dataset as one of three types: a core point, a border point, or a noise point. And understanding these three roles, well, that's the key to the whole thing. To do this, we need to give it two key instructions. The first one is called epsilon, or just eps. Think of it this way. If you're a data point at a crowded party, epsilon is the radius of the circle you draw around yourself. Anybody standing inside that circle is your neighbor. It's that simple. It's just how far we're willing to look for friends. The second instruction is min points. This basically sets the rule for what counts as crowded. So sticking with our party analogy, if min points is set to 5, you need to have at least 5 people inside your epsilon circle to be considered part of a dense group. It's kind of like the minimum number of friends you need to be popular. So with just those two rules, we can define every single point. A core point is a popular person. They've got at least min points friends in their little circle. A border point is on the edge of the cool kids table. They aren't popular themselves, but they're friends with a popular person. And a noise point, well, that's a loner. They're not a core point, and they're not close enough to any core points. They're the outliers. Okay, so we've got our definitions down. Now let's see how this all comes together to build an incredibly powerful clustering process. We're going to walk through the algorithm step by step.
The whole process is actually really elegant. First, the algorithm just zips through and classifies every single point, core, border, or noise. Done. Second, it finds a core point that it hasn't visited yet and says, okay, new cluster starts right here. It then finds all the other core points that are reachable from it and pulls them all into that same cluster. Third, it looks for any border points that are hanging around those clusters and assigns them. And finally, and this is key, any points that got labeled as noise are simply left alone.
And this is where the magic really happens. By following that simple density-based logic, the algorithm can uncover these amazing patterns that were totally invisible to other methods. Let's see the payoff. So let's just quickly remind ourselves of the problem we started with. K-means saw this data and gave us, well, a complete mess. It totally failed to see the real structure hiding in there. And now, look at the result from DBSCAN. It is perfect. It correctly identified the 2 rings, the 2 lines, and that little clump at the bottom. And just as importantly, see those black dots? That's the noise. It correctly identified and separated out the outliers without trying to force them into a group where they just don't belong. So, the crucial point here is that while DBSCN is incredibly powerful, It's not fully automatic. Its success really lives or dies on us choosing the right values for those two parameters, epsilon and min pots. If your epsilon is too big, everything just merges into one giant blob. If it's too small, everything starts to look like noise.
So how do you pick the right value? Well, data scientists have a pretty clever trick for this. They create something called a k-distance graph. What they do is calculate the distance of every single point to its kth nearest neighbor, where k is your min PDS value, and then they plot those distances in increasing order. The ideal epsilon value is often found right at the knee or the elbow of this curve, that exact point where the distance suddenly starts shooting up.
Okay, let's wrap this up and see how this all plays out in the real world. Why does it even matter that we can find weird shapes and isolate noise?
Here's a quick summary. The advantages are huge. It can find pretty much any shape, it's really robust to outliers, and this is a big one, you don't have to tell it how many clusters to look for in advance. The main downsides are that it's sensitive to those parameters we just talked about, and it can sometimes struggle if you have clusters that have very different densities from each other.
And because of these strengths, DBSCAN is used everywhere. I'm talking spatial analysis for finding hotspots of activity in a city. In finance, it's a game changer for anomaly detection, where a fraudulent transaction is basically just a noise point. It's used to segment customers, analyze pollution data, and even identify traffic jams.
So I'll leave you with this thought. Algorithms like k-means are powerful, but they kind of force us to see the world through a single lens, a world that's only made of simple round clusters. DBSCAN reminds us that data can have any shape it wants. And it really begs the question, what hidden stories are we missing out there simply because we've only been looking for circles? Thanks for joining me.